inductors, that's so what do these look like? Coils, okay? So remember, a coil of wire, sometimes we call it a coil of wire, sometimes we call it a solenoid, sometimes we call it an inductor. It pretty much depends on how you're using it, but those are all the same thing. They are just a coil of wire, okay? So, and if you wrap it into a donut shape, what do you call that?
Samala.
No, it's a
They
toroid.
changed it now. They're calling it white.
They're called something else.
They're called a
Yeah.
toroid. Okay.
What are they
Toroidal
Caramel delight.
shape. Okay. All right. Remembering back to capacitance. What was the purpose of capacitance? Storing charge to get what?
Potential energy.
EMF.
All of those things, yes, but to create a constant electric field. Okay. What does a coil of wire give you?
Constant.
A constant magnetic field. It's for storing magnetic energy. Capacitors store electric energy. Inductors store magnetic energy. Okay? And they have a constant field inside them. Although if you wrap it in a circle like a toroid, is that a constant magnetic field?
Oh.
No.
Wow,
Right.
picture your
It's
voice.
gonna change a little bit if you depending on the size of the radius of the circle, but it will give you a circular magnetic field. Because a regular solenoid gives you straight magnetic field lines. If you wrap it in a circle, it gives you curved magnetic field lines. But just like running on a track, right? Some of those lines have to go farther, so the field's a little bit different. Right? It's less. It's more condensed closer in. It's a little more stretched out farther out. Okay. So, capacitance is how much charge can be stored on a capacitor at a given potential difference. This is old news, okay? Inductance, L, and why is it an L? Lens. L for lens. This is not important, but just fun facts, okay? So, how much magnetic flux is created in a solenoid by a given current? Well, inductance is flux divided by current. Okay, this was charge divided by voltage. This is flux divided by current. And what is the unit of inductance? There's a lot of dudes to remember here.
Lenses. Lensi.
It wasn't Lenz. It wasn't Faraday. It was the guy that discovered Faraday's law. Henry. The Henry, which is a Teslameter squared over.
I'm a slight girl in college. I gotta
You
remember
don't
these dudes'
have to
names.
remember this. Well, you do have to remember that the unit of inductance is Henry. So I tell these stories. It gives you one other way to remember things. I don't know if it helps.
Bothers me you didn't capitalize Henry.
That's not me. That's how it's.
Are you serious? Like it's not a name? That is annoying.
It's a unit.
It's still a name.
Here, do you want me to capitalize it?
No, it's fine.
Just changing slides
For my
for you.
English right now.
Okay, so inductor. That's a coil of wire used in a circuit. That is a bad color blue. Okay,
Tesla meters.
so
For me.
what was the
What's the unit? That's pretty good.
just a couple ideas.
Yeah.
If you have a constant current flowing through this thing, does it have an inductance?
No.
No. So what do you need for an inductor to do stuff? Changing current. Okay? And this is self-inductance, because you'll notice we just have one coil, not two coils. So there's two kinds of inductance. You can induce current in another wire, or you can have some current that counteracts the current that's already going through your wire. Okay? So when you have a constant current through an inductor, what does it act like? The current's not changing. That means you don't have any stuff happening. Yeah, it just acts like a wire. So if you just have a DC current going through it, it doesn't really do anything. As long as it's not changing, as long as the current's not changing, you can just treat it as a regular wire. Okay? But if the current is increasing or decreasing, what's it going to do? So let's say the current's increasing. Okay? What's going to happen in the inductor?
It's gonna get smaller. The inductance.
Yeah, so if you have a current going this way, right? Magnetic field's going this way, it's getting bigger. That's going to induce an opposing current and an opposing magnetic field. What does that do when that's in the same wire? Acts like a resistor. Okay? So you get some sort of resistance from this effect. Okay? And the polarity of the resistance depends on if your current is increasing, in which case it opposes it, or if your current is decreasing, in which case it tries to help it along. Okay? So it's a kind of weird resistor. It's a resistor in one direction, in the other direction it's kind of like a little mini battery. Okay? So sometimes it boosts the current, sometimes it slows it down.
So let's go through the derivation for the inductance for a solenoid. So just for a solenoid, we want to remember the magnetic field for a solenoid is just mu n I over L. And remember, the density of the coils is what really matters here, so the N over L factor. Then to use that to calculate the flux, we're going to multiply this magnetic field against the area. You can see the area of each loop should be parallel to the magnetic field, so we don't have to really worry about the dot product. And keep in mind, when we talk about area, we want to go loop by loop because there's more than one loop. So the magnetic field is the same through each loop, and there's more than one loop. So we'll start by writing down the magnetic field through just one loop. Okay, so that's our B solenoid, so we'll write that here. And that's mu Ni over L. And then we'll figure out what we need to do with the area since the dot product's already gone away. So we need to do each loop. So if we have 4 loops, that would be 4 times the area of one loop. But we'll just generalize that to n times the area of one loop. Okay, so that includes all of our loops. In this case, this looks like 4, but we just want this in general. Okay, so we multiply that through. Now we have an n squared. Remember, we're writing mu and not mu naught because mu naught is for a vacuum, meaning there's nothing inside the coil, but you could hypothetically put a material inside the coil and then it would have a magnetic permeability mu. So if we want to calculate inductance, we just take this flux that we calculated for the solenoid and put it over the current, and that's just going to take what we have and cancel out this current. So you get mu n squared A for the area over L. And that's the inductance for an ideal sort of infinite solenoid.
This is the inductance for a solenoid. Okay? So remember, capacitance dependent on what?
Area.
Length, yes, length. So what are the things that, so the definition of capacitance is the ratio of charge to voltage. Okay, that's what a capacitor can store. But what determines that ratio?
Distance between the area and
Your geometry of your capacitor, so yes, your area and your distance between the plates, okay? But, I mean, that varies, because you can have those concentric spheres, right? So it's not necessarily area. So always geometric concerns from the way that the capacitor is constructed, and also the material between the plates, right? The dielectric strength, okay? For an inductor, this is the inductance. And what does it depend on?
Number of turns.
It's the length of the solenoid, the number of turns, right? The area and permeability, which you could imagine can sometimes be just mu, which is some multiple of mu naught.
Did you tell us what that was? Did we do mu?
What mu naught was?
No, just mu.
No, we haven't talked about that. And actually we're not going to because we don't
No, I
really
could've
deal with it too much.
I could have sworn that you gave
Yeah, it's a
us
lot like kappa. But we don't, I mean, I guess, well, we can talk about it. Mu is like when you put iron inside of a solenoid, right? That changes the way that it
Oh,
works.
no. You gave it to us as a vector. That's why. That's what I was thinking of.
That is the magnetic dipole, which is something different. Unfortunately. But it has the same
Same fucking
symbol,
letter.
so just don't get confused. Like we just did.
Yeah.
Don't do that. Okay. So divide it by the, what was it, the current? Yeah. So just like when we calculated capacitance, we figured out what delta V was, and then we just put Q in. Okay, so we had Q divided by delta V. In this case, we're going to calculate the magnetic inductance, and we just divide it by I. Okay, and you'll end up with something like this. Now, this is just for an infinite solenoid. Okay, and this comes partly from. Do you guys want to go through the derivation?
No.
Okay. Basically, you use the magnetic field of an infinite solenoid. You multiply it by area. You do that whole thing, and then you divide it by the current. That's it.
Did we do the magnetic field for an infinite solenoid?
Yes. We did it in lab too. Right?
Okay.
So I'm gonna do the derivation.
we got a lot
Like a non-consensual derivation. Okay. So what's the magnetic field of an infinite solenoid? I mean, you used it on Tuesday.
Not I over 2 pi.
No, that's a loop.
Yeah.
Okay. Right, it's as an infinite wire, so we need. Okay.
And over.
Okay.
What it was.
So if we want to figure out the magnetic flux, that's AB cosine theta, AB cosine theta, but remember the cross-sectional area of each loop should be parallel to the magnetic field. Okay, the area vector at least, because the magnetic field points this way, and for each loop the area vector points this way, so the cosine theta goes away in this case, and we end up with mu naught I n over L, that's B, times A, but how many A's are there? How many areas are there? N, right? Because
Yeah.
every loop has an area. So N times the area of your loop. Okay, so that's your magnetic flux. It's magnetic field times area.
Okay.
Okay? And then inductance is the magnetic flux divided by current. So all you do is get rid of this. Okay, so you end up with mu naught n squared A over L. Okay, so that's where that comes from. Okay.
How do they keep the wires from coming?
Okay. Yeah.
together?
Well, usually they're touching.
Okay.
Yeah. Like if you look at the solenoids we have, they're coiled, so they're together already. So yeah. So you don't have to keep them from touching because they're already touching. Yeah. So yeah, this is the number of turns. This is the cross-sectional area of one of your loops. This is the length. Okay. And what does it depend on?
What does the length depend on?
And what does inductance depend on?
Oh.
The number of turns, the length.
Geometry and material. Okay? Just like a capacitor depended on geometry and material. Alright? And not the material that the wire's made of, but the material inside the device. Okay? So capacitor, dielectrics in between the plates. If you have any kind of magnetic material inside of your coil, that's going to be what we're talking about. Okay, so inductance depends on the geometry and also the material.
So that's a lie. Depends.
Well, so
only.
I haven't in the past been covering the metal cores, but and since we changed that lab, now you've already seen that. So it's worth talking about where that goes in the equation. Okay, I will change the slides. Oh my god. Actually, I think technically I owe you extra credit for pointing out all the mistakes, but.
I need it, so. Work that shit
All
over.
right. So when current is steady, we already decided that this will just act like a wire. Okay. But if current isn't steady, so let's say we have an increasing current. Right? That means our induced, so that means our original field points this way. Okay, and since it's increasing, our induced field points this way, which means our induced current goes against the original current. Okay? If you go the other way, just the opposite happens, right? In this case, you have current going this way, it's increasing, that means your induced current goes the same way. And what this does is it changes the polarity of the delta V. Okay? And delta V is the voltage drop or not drop across this thing. So in this case, it acts like a resistor. In this case, it acts like a little battery. Okay? This is boosting your current. This is slowing it down. Okay? And if we want to figure out what delta V is, that's just the inductance times the time derivative of the current.
The absolute value.
Technically there's a negative here, but just like before, I have it as an absolute value because I want you to figure out the signs separately.
Oh, so like conceptually.
Yeah, because so much of the time it depends on how the circuit's set up, that just automatically adding a negative sign is not the whole picture. Okay? All right. Let's take a break and then we'll talk about the rest of this.
The coolest name I've ever heard. His name
Stone.
was Stone Smart. I'm like, dude, yeah, you're
Stone
badass.
Smart.
Yeah, it's fucking awesome. Smooth, dude. But I'll never forget, he played quarterback and
He
like
needs his own line of
he
cologne.
just I don't know, he just like Russell Wilson the fuck out of this one dude and like, have you ever seen somebody get juked so badly that their shoes fall off?
Oh.
Yeah, like legitimately tied cleats off, and then he just fucking hucked it like 50 yards in the air, and I like shit a Twinkie. I was like, oh well, I'm not gonna win this one. Yeah, it was bad.
All right. So, remember, when we have resistors, if the current's going this way, right, what's our voltage difference?
Negative.
Negative IR. Okay, so it's a negative voltage difference because you're going in the same direction as the current. That's how resistors behave. So this is just a reminder. For inductors, if the current is decreasing, right, that means the downstream end of the inductor is at a higher voltage. If the current is increasing, the downstream, like meaning downstream from the current, okay, end of the inductor is at a lower voltage, okay? And so delta V opposes the change in current. What this means is if you have an increasing current, it acts like what? A resistor. Okay, so an increasing current
We got there.
acts like a resistor. So is this negative or positive?
Negative.
Negative, exactly like the resistor, and this should be positive, and delta V should be negative, okay? So that's why I said we're doing it this way. We're showing you how we get the signs. That's why that was absolute value before.
Because it's just opposing.
Okay? So if you're going with the current, and the current's increasing, this thing acts like a resistor. Okay?
Right.
If the current's decreasing, which side's positive, which side's negative?
Positives on the bottom.
Positive on the bottom, negative on the top. What does that look like?
Battery.
A battery. Okay, so that gives you a little boost. Your delta V, right, should be equal to positive L di/dt. Okay, so the inductor will act like a battery in that case.
Big L
okay?
is just length, correct?
Yeah.
Okay.
So this one acts like a resistor if your current's increasing. This one acts like a battery if your current's decreasing. So you're always opposing the change. So if your current's decreasing, it boosts it with a battery. If it's increasing, it creates a resistor. Yes?
So L, is that the length of the whole wire or just a section of the coil?
L is the inductance,
Oh, okay.
which is that thing.
Gotcha. Okay. Good to know.
So, but you don't usually have to calculate the inductance, right?
Wait, is that
Just
DI
like,
or
what?
DI.
it's DI? Okay. Yeah.
Just like in most cases it'll be given to you.
Okay.
But sometimes if you're making your own inductor, then you have to actually plug in the numbers.
I hope I don't have to do that.
Well, it's not that hard. You just go like this. Okay.
Just paper clip it out.
You can do it. I believe in you. All right. So let's try putting the positive and negatives on these guys. All right.
This should be that one. Current is increasing. Yeah. Current is increasing.
All right. So here we have current going up and it's decreasing. Okay. So what should be here?
Plus.
Plus. What should be here?
Minus.
Minus. That pushing current the same way. Okay? Over here, minus plus, that acts like a resistor. It's going to slow the current down by resisting it, obviously. Okay, over here we just changed the direction of the current, but it's the same concept, right? This is an increasing current, but it's going down. So this should be minus, this should be plus. This is now the decreasing current, but it's going down. This should be plus minus. Okay? Okay. All right. So, what do we mean by voltage A is greater than voltage B? What does that mean in terms of plus and minus?
Plus, minus.
This side is plus, right? This side is minus. From the previous problem, whether or not we got it correct, we know that two of them are going to give us that configuration, right? So you can either have an current from B to A, so either a current this way, that's decreasing, okay, or a current this way, that's increasing, all right? Both of those will give you plus, minus.
And what?
What?
Do we?
What's the answer?
Oh.
E.
It's E.
You son of a gun. You were right.
All right.
Damn it! Why did I change it?
There's like 3 correct answers, but remember, multiple choice is the best answer.
It's the most correct.
The most correct.
The rightest answer.
Which is
Fucking
why
stupid.
we don't do multiple choice tests, because I think those are
Ridiculous.
stupid.
Which orange is more orange?
And now we have partial credit, so if you're only kind of right, you still get points, just not as many. Okay. All right. So remember, in a capacitor, we stored what kind of energy? Yes, but what kind of, where was the energy stored? In the electric field, okay? Energy is stored in the electric field, all right? In an inductor, we also store energy, and it's stored in the magnetic field, okay? So this is the energy stored in the capacitor. This is just review. This is the energy stored in an inductor. It should look pretty similar, okay? So we're not gonna, the derivation is basically the same, so we're not gonna do it this time. And just generally, right? Electric fields, magnetic fields. Electric fields, we use a capacitor to store energy. We use a capacitor to create a constant electric field. And remember, this is your energy density, and it's from the electric field, okay? For an inductor, it's pretty much the capacitor of the magnetic field. So you have potential energy from the inductor, and you store that energy in the magnetic field, okay? So we don't end up using these a lot, but it's important to be able to see mathematically that this statement has like a mathematical component to it. All right. When we say the energy is stored in the field, that's not just like philosophy; it's math too.
I would hope so.
Well, the main difference between physics and philosophy is math and being able to
Prove.
test things.
Prove,
Yeah, have
right?
proof.
Yeah, proof, yes. What's the saying in science? Everything after physics is just an opinion.
Yeah.
Is that a saying? I feel like that's only a saying for